Alright, so today we're going to talk about stochastic processes, but before that we need to explain the difference between random and stochastic. So let's just say you're playing Monopoly, and when you roll the dice you generate a random number. We use those random numbers to move my player around the board, and the position of the player is a stochastic process.
Okay, so as I was saying, the stochastic process has to do with the time evolution of a random variable, and that random variable may be discrete, like the dice example, or it may be continuous, like the position in physical space. The state space and the time may both be discrete or continuous. Stochastic processes are very common in physics and chemistry. If we break the types down into discrete and continuous for the time axis and discrete and continuous stochastic processes for the state space, then we can kind of categorize the family of different frameworks for thinking about stochastic processes as follows. So you have discrete master equations, which describe a continuous time evolution in a discrete state space. Examples of these things that you may have heard about that we will learn in the class: kinetic Monte Carlo, some transitions between states, pump probe, these kinds of things, all have to do with spectroscopic processes and the transitions between discrete energy levels and molecules. Survival probabilities are a common one, where you think about watching a system and waiting for the first event to happen, like you might do in a nucleation experiment. In continuous master equations, we're thinking about a continuous time variable with a continuous state space. You can generally formulate these things so that you have very non-local transitions, but most of the time when you encounter these in physics and chemistry applications, these continuous master equations are often in the form of a Fokker-Planck equation. And those are very common in thinking about processes like nucleation and growth, population balances, polymer dynamics, things of that sort. Now, there are many situations where it's convenient to go ahead and discretize the time variable. And of course, you lose a little bit of resolution and ability to do certain things, but as long as you didn't care about that discretization, then that's okay. And one of the really prevalent applications of these is the Markov state modeling work, where you have a discrete time axis and a discrete state space. And examples in physics and chemistry where these are very important is in studies of protein folding and all kinds of biomolecular transitions. And then there are also cases where we have a discrete time axis and a continuous state space. These are less common, but one of the cases that is becoming more prevalent is the work on Green's function reaction dynamics. We probably won't get to that in this class. To model reaction diffusion processes in cells, where you have both the importance of you want to keep track of the positions where every molecule is, but there's not very many of them, and you can afford, in many cases, to do this kind of description much better than a kinetic Monte Carlo description. Okay, as we're getting started here, we're going to think about just defining some vocabulary terms. We're going to talk a lot about Markovian processes, and these are special stochastic processes where the future depends only on the present, independent of all prior history. And these are important, of course. You may have seen them in molecular simulation classes before for things like Monte Carlo simulation, and we'll think about these in the context of kinetics quite a bit as well. The next term we're going to talk about here is metastability, and that refers to the lifetime of a state that's long enough to prepare it and define its properties. So I'm going to stop short of saying that it's long enough to measure its properties. Okay, I want to use this example of a nickel 100 surface and H atom diffusion on that surface as an example to illustrate what I mean by metastability. Okay, so if you think about the XY plane here, of course there's a continuous range of positions where an H atom could sit, but we know that they like to sit in these hollow sites, and so maybe at a given time you might find it sitting here, for example. So this is my H atom starting right here, and if we track its trajectory over time, it might sit here and vibrate around in this little site for a little while, and these are vibrating too, so these oscillations here are going to be rather irregular. And once in a while it'll get activation energy and it will pop over into a neighboring state, and now it'll live in this state for a little while, and maybe it misses that one and ends up all the way over here and then pops out into this one and then into this one and eventually off the page, and we'll stop tracking this. But the point is that it really doesn't spend much time here in these bridging sites. It jumps from one hollow to another, and it kind of does a random walk in a quasi-discretized kind of version of the original XY plane here. So this has effectively been discretized into one state that's here, one state that's here, one state that's here, one state that's here. And of course, there are a bunch of other states that it didn't visit. But the point is that we can effectively think about the trajectory of these H at atoms as a random walk on a discrete lattice of metastable states, instead of thinking about the specific XY positions and just recording time everywhere. And this is a tremendously powerful tool for coarse-graining dynamics. If you think about what you need to simulate the dynamics of this random walk process, all I need to know now is the lifetime and the probability of jumping from one state to a neighbor. And if all of the neighbors are equivalent, then this becomes a really easy problem of throwing dice, and I only have to throw enough dice to generate how long it will live here and which state it will jump to, and that's the basis of kinetic Monte Carlo. The whole process works because of metastability. Each of these little states survives long enough that it kind of forgets how it arrived there and what its conditions were when it came in before it makes another hop. And so, in a sense, each of these states has characteristic properties, including a statistical lifetime with an exponential distribution of escapes that allows you to really replace F equals ma for these kinds of processes and really accelerate things. And what's remarkable is that if you ran F equals ma and then you went back and compared that to a kinetic Monte Carlo simulation, which might be 1,000,000 times cheaper, and that's not an exaggeration at all, then you would find that the statistics of the random walks that you saw with the expensive simulations would look exactly like the statistics that you see for the kinetic Monte Carlo simulation. Okay, let's begin working on a quantitative framework for describing stochastic processes, and we're going to begin with the discrete master equation. Okay, so when I write M equation throughout these notes, I'm referring to a master equation here. The idea now is that we're going to have a discrete state space. We're going to number our states 1, 2, 3, ... out to n, and we're also going to talk about the probability that the system is in state J, which we're going to write as Pj of t, and we're going to have to introduce transition frequencies. These are frequencies of making a transition from state I to state J. Notice the notation here. We're going to write omegas, but the index where we're starting is over here on the right, and it goes to the index on the left. Another note about this is that these are the frequencies of these transitions given that you're actually in state I. Okay, so when we're formulating these, it's important to remember that little tidbit. The last bit is that we have this idea of a probability balance equation, which is the master equation, right? So you guys are all familiar with mass balances and momentum balances and species balances and things, but the same thing applies to probability. It can't actually disappear. So if we enumerate the whole state space, then we have transitions from one place in the state space to another, but the whole probability that we started with is always still there. And so we're going to be able to write down a probability balance equation, and that is our master equation. Okay, so our probability balance equation is that the derivative of the probability to be in state J with respect to time is the sum over all other states of the probability to have been in those other states times the transition rate at which we're going from other states to J. And then we also have, so those are all the things that are coming to state J, and then we also have flow out of state J. So that's the probability that we're in state J times the transition frequencies to go from state J to all other possible states I. Now there's really not anything so mysterious here. This term on the left is the accumulation of probability in state J, and it is comprised of the flow in to state J minus the flow out of state J. Now, the next step is for us to put this into matrix notation. And if you look at the structure of the flow out term, it's diagonal, right? So it's telling you how the probability of being in state J changes due to the probability of being in state J. And this one is having to do with the probability of state J changing due to the probability of being in other states, these flow in terms. Okay, so that kind of gives you a guide of how these things go into this matrix form. What we're going to do now is we're going to just write this down as a probability vector. So this is an in-component vector if we had an in-length state space. And so the derivative of that probability vector with respect to time is going to be a matrix acting on that probability vector. And I put a minus sign out in front of my W matrix. Some books do, some books don't. I think it's a little more convenient to think about the rate constants in that way. What are the elements now? How do we arrange the matrix elements in here so that we get an equation? The goal, of course, is to recover this equation line by line out of this matrix. If I multiply this thing W by the matrix P, I have to get the left-hand side of this equation. And it's really just a matter of bookkeeping, putting this all together. But the idea is that all of these flow out terms, they're on the diagonal. Okay, so for example, if I want to write down dpj dp2 dt, that would be the second line in this matrix, and that's going to involve the second, so I would have a p1 and a p2, and I want this whole sum of everything leaving state 2 going to all other states to multiply p2, so it should be in the second place, and all of these non-diagonal terms, the flow-in terms, are telling you how state 1, how fast state 1 comes to state 2. That should multiply the P1 term. I'll have a P3 below this, and that would sit over here. And I keep going all the way till I get to the bottom. The Pn term might have some probability, and that will be going with this rate, omega n goes to 2. I put the minus sign in there, remember, so that when I have the minus sign out front, it's going to end up giving me a positive sign. And that's really because processes that only leave a state then end up looking like they have, like an A goes to B kinetics, for example, will have a rate constant, and you write down this rate law, and it looks just like the derivative of A is equal to minus some constant times the probability of being in state A. And the minus sign for me makes these equations look a little bit more like standard kinetics. Okay, now one thing to be careful about, in these sums, you can see they're not restricted. And so we're technically summing over a rate of a 2 goes to 2 transition, for example, inside this summation, and n goes to n transition inside this one. There is no transition frequency for not making a transition. And so we define these omega I to I rates as 0 for all of the i's. Now once we have this matrix set up, we've done all the rate calculations to fill in all these omegas, then the solution to this becomes pretty simple, at least formally. It is the probability at time t is e to the minus wt, so this is a matrix sitting in here, a rather complicated one, I suppose, that then acts on my original probability vector at the initial time and gives me back this probability at a later time. Okay, there are some familiar tricks for solving these kinds of things. First of all, you want to diagonalize this W matrix. So if you know the eigenvectors of the W matrix and the eigenvalues, this is the diagonal matrix of eigenvalues, lambda. And if I have my S matrix contains column eigenvectors of W, then my S to the minus 1 is its inverse, and that's what it really just means to have diagonalize this, is that I can sandwich this thing between S inverse and S, and it gives me that diagonal matrix of eigenvalues. Now the eigenvalues tell you the natural time constants associated with decays from one state to another in this complex state space. And you see that they're all sort of exponential decay kinetics. You can see that they're exponential. I guess I should explain why, because we have this exponential operator here. Now if we expand this W matrix using the same tricks here, a little bit more complicated, and I won't go through it in this video, but we can change this e to the minus W T matrix into an S e to the minus lambda T S inverse matrix. And then you see that effectively what you've done is you've taken your initial probability vector, resolved it into the eigenvector basis, operated with the eigenvalues in this exponential. So now all of them operate independently, and ones that decay very fast will disappear. Those are going to be the very fast transitions in the network. And then ones that take a very long time to equilibrate will live for a long time decaying. And that's all in this eigenvalue structure with the 1 over lambda I. So very small eigenvalues correspond to very large time constants. And that's now going to give us the probability as a function of time, also resolved into the eigenvector basis. Then, of course, to recover the original coordinates, you just multiply this thing by the original matrix of eigenvectors, and you'll get, these two will cancel, and you'll get your probabilities back in the original basis.